In these coming videos, we're gonna talk about a very important theorem on dimension of fibers. Suppose we have a surjective morphism pi from an irreducible F1 variety Y to an irreducible F1 variety X. Then we claim that for every point P in X, the dimension of the fiber above P is gonna be greater than or equal to dimension of Y minus dimension of X. And actually for most P, this is going to be an equality. Now when we say for most P, what we mean is that there exists a non-empty open set U in X such that for every P in U, dimension of the fiber above P is exactly equal to dimension of Y minus dimension of X. Why is this the same thing as saying for most P? Well, because X is irreducible, so every non-empty open subset is dense. And so this statement says that the equality actually holds for a dense open subset of X. So in this video, we're gonna cover this inequality, and we'll prove this second statement in the next video. For this, we'll need to recall Krull's High theorem, which says that if X is an irreducible F1 variety, and Fi's are regular functions on X, then the common zeros of the Fi's in X is gonna have codimension less than or equal to S. In other words, each polynomial can cut down the dimension of X by at most 1. So now coming back, let us suppose that the ideal of functions regular function on X vanishing at P is generated by F1 ... Fs. In other words, P is a common zero set in X of the function F1 ... Fs. By Krull's High theorem, we know that each of these functions can cut down the dimension of X by at most 1, so this set is of dimension at most S. However, since P is only a point and X is irreducible, the codimension of P is exactly equal to dimension of X, and thus we have dimension of X must be less than or equal to S. Now to find out the dimension of the fiber over P, we also want to write it as the common zero sets of some polynomials over Y. And we claim that it's exactly the zero set in Y of the pullback of the Fi. Indeed, a point Q lie in this fiber if and only if pi of Q is equal to P. But this set, the singleton set P, is uniquely characterized as the common zeros of the Fi. So pi Q is equal to P if and only if pi Q is the common zero of all the Fi, or equivalently if and only if Q is the common zero of the pullbacks of the Fi's. Thus we see that the fiber over P could be cut out by S functions. So again, by Krull's High theorem, its codimension in Y must be less than or equal to S. Or equivalently, the dimension of the fiber over P must be greater than or equal to dimension of Y minus S. But recall that S is greater than or equal to dimension of X. Thus, we see that the dimension of this fiber must be greater than or equal to dimension of Y minus dimension of X. And this was exactly what we claimed to show. In the next video, we're gonna show that equality is gonna hold on an open dense subset.